Hello everyone, welcome to B.Tech. Today in this session we are going to discuss about discrete cosine transformations, which is nothing but the Fourier transformation, which is a combination of sine and cosine functions, right? So here we are going to discuss about discrete cosine transformations DCT, and its inverse is also considered here. So this is a transform that is similar to Fourier transformations, which I have earlier said. And this is in the sense that the new dependent variable represents again the frequency component, and the DCT is given here with a mathematical formula. C of u is equals to a of u, where the function is dependent on the u value, and summation x is equals to 0 to the maximum value n minus 1. F of x is the main function which we are going to transform, and this is the multiplicative cosine function cos of 2x plus 1 into u into pi by 2n, where u is the variable, right, dependent variable, right? So this is varying from 0 to n minus 1. This is the initial value and this is the final value. So this is considered here, where this a of u, right? So this a of u is a dependent variable, is a parameter that is defined as square root of 1 by n into when u variable is starting from the initial point of 0, the value will be square root of 1 by n. If this value starts from 1, then the value will be square root of 2 by n, because if we consider the initial value, there will be no subsequent coefficient. If we start this from the preceding one, then it will be having some sort of coefficient value. So this a of u parameter is defined as a of u is equals to square root of 1 by n if u is equals to 0, square root of 2 by n if u is starting from 1 to maximum value of n minus 1. So this is the discrete cosine transformation, as we discussed in earlier classes, that the discrete cosine transformation or the discrete Fourier transformation will be a sum of the sine and cosine functions with the frequency components multiplied, and finally we will be retrieving the original transformation of an image or the transformation of the signal, right? So here we are considering that cosine function as cos of 2x plus 1. These are the frequency components with the main component u pi by 2 into n. So this is the cosine transformation, right? So now we are having the inverse. Automatically we will be discussing about the Fourier forward and reverse transformations. So now we are considering the discrete cosine transformation in inverse. So that is defined as IDCT, inverse discrete cosine transformation. So for this we are considering the function as f of x here, and previously we have a of n. We are considering f of x here. So this f of x is equals to summation u. Here the component is u dependent variable. U is equals to 0 to n minus 1. A of u into c of u into, this is the cosine transformation function cos of 2x plus 1 into u into pi by 2 into n. This is the components we are taking. The maximum value is n minus 1. Next value is n. Next value is 2n. So this value will be considered here. Clear? And now the two-dimensional signal or the two-dimensional images will be calculated with these two following mathematical equations. First one we are discussing forward, and the second one is inverse, right? So this is for forward and this is for inverse. Forward DCT and this is inverse DCT. So C of u comma v, two variables, two-dimensional, right? So two variables we are taking here. U comma v is equals to a of u into a of v, summation x is equals to 0 to n minus 1, y is equals to 0 to n minus 1, f of x comma y, cosine function of the same frequency component. It will be repeated for both variables x and y. And for inverse also we are taking u of u is equals to 0 to n minus 1, v is equals to 0 to n minus 1, a of u into a of v into c of u comma v with the function of f of x comma y. We are taking c of x comma y. This is the function, right? So this is we are considering here, and we are considering two cosine functions. One is for x coordinate and second one is the y coordinate. This is for cos of x coordinate and this is for cos of y coordinate. Both we are multiplying here. So this is the two equations we are representing for discrete cosine transformation in forward and discrete cosine transformation in inverse. Clear? So these both mathematical formula or the mathematical representation for both forward and reverse will be remain same for discrete cosine transform, discrete Fourier transform, or discrete sine transformation itself. Clear? So coming to the properties of this discrete cosine transformations, we have a few properties, very important properties we will be discussing here, and observe carefully each and every point. I will read aloud and I will explain you clearly. Clear? So the first one we are going to this properties is the cosine transformation is real and orthogonal. So what is this real? So real in the sense it is not having any type of imaginary components or any type of imaginary values. It is having a real value. That means if A is equals to B, then B value will be varying from 0 to n minus 1, or it will be varying from 1 to n. So that's it. But what is about non-real? Non-real means it is having some type of imaginary components. That will be like A is equals to IB, or A is equals to C plus IB, where this I represents the imaginary component, and this is not the case which we are discussing here. Clear? So this is real and orthogonal. Orthogonality in the sense perpendicular. Next, the cosine transform is not a real part of the unitary discrete Fourier transform. The cosine transformation is not a real part of the unitary discrete Fourier transform. Unitary in the sense it is having only the single variable component but not the two variable components. And the cosine transformation of a sequence is related to discrete Fourier transformation of its anti-symmetric extension. So always the sequence will be in the form of symmetric extension or symmetric expansion only, but not in anti-symmetric expansion. So the cosine transform is the fast transformation. Cosine transformation is fast transformation from one transformation to the other or remaining transformations. That means from one form to another transformations. Any other form we can transform it very easily, and if we want it in reverse also, it will be transformed very easily and very fastly, very quickly. And the basis vector of the cosine transform are eigenvectors of the symmetric tridiagonal of topologic matrix. Here we are considering the eigenvectors. What are eigenvectors and what are eigenvalues? So this will be explained in the further topics very clearly with examples. But as per of this here, eigenvector is the knowledge we are sharing here for basis vectors. And the cosine transform is close to cosine transform is close to KL transformation, and this is one form of a transformation, image transformation. And the first order Markov sequences. The cosine transform has very good to excellent energy compaction property of images. So this is one type of property. And the DCT is a real transform. This property makes it attractive in comparison of Fourier transformation. So we are having various types of Fourier transformations, right? So we can compare each Fourier transformation into remaining other transformations, but it will be resultant as the same. And the DCT has excellent energy compaction property. For that reason, it is widely used in image compression standards as for example JPEG. There are fast algorithms to compute this DCT similar to the FFT for computing DFT. See, here we are having three terminologies: DCT, DFT and FFT. So what is DFT? DFT is nothing but discrete Fourier transformation. DCT is nothing but discrete cosine transformation. FFT is nothing but fast Fourier transformation. So we are using this DCT, that means discrete cosine transformation, because we are using this in the form of an application for digital image processing in the form of image compression, because we are having more accuracy for reconstruction of original image or original signal. You all are very clear about this, right? So the Fourier transform is used for edge detection And this cosine transformation is used for image compression, where the image is compressed at the transmission side and where the image is expanded at the receiving side. And this discrete cosine transform is used for image compression. So clear, right? So DCT, Fourier transformation is for edge detection. DCT is for image compression. Clear? So this is about the discrete cosine transformations, and these discrete cosine transforms are more useful in nowadays with the application of digital image processing is spreading more in day by day. So this is very helpful for us and have a knowledge about this. Clear? Fine, then in next classes we are going to discuss about the remaining transformation of images. How do we transform them and what are the mathematical expressions we are going to discuss in the next session. Thank you.